Hi friends, welcome to my another video. Today in this video, I will discuss how to calculate the prospective fault current of an electrical system. Before going to the deep calculation of prospective fault current, let us understand first what is prospective fault current and why it is important to calculate the prospective fault current. There are two types of prospective fault current. The first one is the prospective fault current due to short circuit, and second one is the prospective fault current due to earth fault. In this video, I am focusing only on prospective fault current due to short circuit. So what is prospective short circuit fault current? The prospective short circuit fault current is the utmost current, the maximum possible current that can flow between the line and neutral conductor for single phase power supply system and between the line conductors for three phase power supply system. Let me elaborate this. Suppose I am taking an example of single phase supply, and this single phase supply is connected with one motor, single phase motor. Due to something wrong happen in the motor winding insulation, the motor will create the short circuit condition, and this due to this short circuit condition there will be a high current in the circuit. Suppose at the full load condition motor is taking only 100 ampere of current, but due to short circuit condition occur in the motor, there is 2000 ampere of current is flowing through the circuit. So this condition is called the short circuit fault condition, and you can observe here that there is 20 times more than full load current is flowing through the circuit, which is very higher. So this current, this 2000 ampere is the short circuit, prospective short circuit fault current for this motor. So it is very important to break this short circuit current as early as possible when there is a short circuit condition occur in the motor. In order to break this short circuit current, we have to provide one circuit breaker which should not only protect the motor from the overload condition but as well as from the short circuit condition. Until and unless we will not have an idea for the prospective fault current for this motor, till then we cannot design a circuit breaker in order to break that prospective short circuit fault current. So hope you got the idea what is prospective fault current and why it is important to calculate the prospective fault current. Suppose if this motor have a prospective fault current 2000 ampere and we place a circuit breaker which have the breaking capacity as 1600 ampere, then what will happen? This circuit breaker will unable to break this current because the breaking capacity of the circuit breaker is only 1600 ampere, but the prospective short circuit fault current for this motor is 2000 ampere, which is higher than the breaking capacity of the circuit breaker. In that case, what will happen? The motor will catch fire and the circuit, the cables also will get damaged. In circuit breaker, apart from the nominal current rating of the circuit breaker, you will find the short circuit breaking capacity of that circuit breaker. Here you can see that the ICU, ICS and ICW is all the short circuit breaking capacity of this circuit breaker. Of course, there is a difference between ICU, ICS and ICW, which I explained already in my air circuit breaker nameplate detail, but these all are related to the short circuit breaking capacity. Here you can see that the ICW is the short circuit withstand capacity, which is given as 50 kiloampere for 1 second. How we selected this circuit breaker? By checking the maximum prospective fault current of that electrical installation, and then we selected the circuit breaker higher than that maximum prospective fault current for that electrical installation. Not only the circuit breaker, but the other equipment in the switch gears like the contactors, overload relays, bus bars, etc. all should be having the short circuit breaking capacity higher than the prospective short circuit fault current of the system, because these equipments also has to deal with this prospective short circuit current at the time of short circuit. So hope you clearly got the importance of calculating the prospective short circuit fault current for a electrical system. Now let us check where you find this prospective fault current in the electrical single line diagrams. This is the SLD for one of the project. Here you can see that the short circuit fault current rating is given as 50 kA for this bus bar. In same manner, the short circuit breaking capacity of this breaker is given as 50 kA, and same for the other breaker, 50 kiloampere, 50 kiloampere. So we can say that at this MdB level, the maximum prospective fault current, short circuit fault current is 50 kiloampere or less. That is why all the components of the MdB has the short circuit current rating as 50 kiloampere. So in case of the short circuit, the maximum prospective short circuit current can be handled by this bus bar and the breakers. If we will check the outgoing loads of this MDBs, then we will find that the breaker short circuit current capacity is given as 35 kiloamperes for SMDBs. It means that at the SMDB level, the maximum prospective short circuit fault current is 35 kiloampere or less. If we will refer the final distribution board breaker short circuit capacity, which is feeding from this SMDBs, then we will find that it could be 20 kiloampere or 25 kiloampere, because the prospective short circuit fault current at the final distribution board level is maximum to be 20 to 25 kiloampere. So it is very important to find the prospective short circuit fault current at the each relevant position of the electrical installation, like at the MDB labels, at the SMDB's labels, at the final distribution load levels, and sometime at the load levels also. So in this video, we will try to learn how to calculate this prospective short circuit fault current in order to design the breakers, the bus bars, the overload relays, the contactors. Let us check another example, and then we will finally proceed for the calculation of short circuit prospective current calculation. Here, this is the GA drawing, general arrangement drawing for the MDB panel. This MDB panel is fed from transformer, and the secondary winding of the transformer and the main incomer of the MDB is connected with the 630 square mm cable, 1 core, 7 runs. Here you can see that the prospective fault current is given as 65 kiloampere for the incomer of the MDB, and for the outgoing breakers of the MDB, the prospective short circuit fault current is given as 36 kiloampere. If we will check the this is the another outgoings of the same MDB, then you will see that the short circuit breaking capacity of the outgoing cable is 36 kiloampere, and some have 50 kiloampere. So it means that for some of the loads, the maximum prospective fault current is 36 kiloampere, and for some of the load of same MDB has the maximum prospective fault current is 50 kiloampere or less. It means that from a same panel, the different load may have the different prospective short circuit prospective fault current. I hope I gave you this example in order to understand you that It doesn't mean that one panel all outgoing will have the same prospective fault current. It may be different. When I will calculate the prospective fault current, then you will understand how the prospective fault current for the same panel outgoing is different. Let us quickly overview what are the reason of short circuit fault. That is, first reason is overloading for the longer duration. If you are overloading the motor for the longer time, then the winding insulation of that motor will burn and it will cause the short circuit. So one of the reason is overloading. Second reason is insulation damage. Suppose someone hit the cable and mechanically the insulation of the cable damaged, then it may cause the short circuit. The third reason is aging and outdated wiring. Every electrical equipment has some age. If you are using that equipment more than that age, then it can cause the short circuit fault. The other reason of the short circuit fault is loose connections. If you will make any loose connections in the electrical installation, then it will heat up very early and it will cause the insulation failure due to that heat, and which may cause the short circuit fault condition. The other reason of short circuit fault is dust and moisture. If in your electrical switchyard there is too much dust and moisture, then it also can cause the short circuit condition. The other reason is insulation failure. As I told you, suppose when we are providing a load to a motor and that motor is running with more than its full load current, then after long time the insulation which is provided in the winding will get damaged due to the overheat and it will cause the short circuit condition in the motor. So the insulation failure is also the cause of short circuit fault. Accidentally touching conducting material. Suppose in the transmission line, if snakes or any bird or any animal touches the two conductors at a time, then it may cause the short circuit condition. The other reason is physically touching two different lines. Suppose in the transmission line or in the panels, if the two phases are touching each other, here it can touch by the huge sags or due to the wind. As I told you in my discussion that we have to calculate the prospective short circuit fault current at the each relevant position in the electrical installation. So in this video we will calculate the short circuit prospective fault current at level 1, level point A, point B, point C and point D. I have taken an example that this transformer has a ratio 11 by 0.415 kV, 2000 kVA rating, and the percentage impedance is 0.548. This is the main distribution board. This is sub-main distribution board which is fed from this MDB, and these are the final distribution board which is fed from the sub-main distribution board. Here I have taken 7 cables of 630 square mm single core. Okay, 2 for red phase, 2 for yellow phase, 2 for blue phase and 1 for neutral. And the outgoing cable for this SMDB is 240 square mm cable. In same way, I chosen this cable as 25 square mm for from sub-main distribution board to the final distribution board. Now, how we will get this data? Transformer, you can get it easily from the transformer nameplate. Here you can see that this is 2000 kVA transformer and it has the percentage impedance from 5.48 to 6.15, and the secondary current is given as 2782. The voltage is, primary voltage is 11,500 to 6,900 and the secondary voltage is 415. The primary current is 100 when the transformer is set at 11,500 volt, and the the primary current is 167 when the transformer is set at 6900 volt. So this information you will easily get from the transformer. The transformer percentage impedance is very important factor in order to calculate the prospective short circuit fault current for the electrical installation. Here the available data is transformer kVA, that is 2000, percentage impedance 5.48, secondary voltage 415 volt or 0.415 kilovolt, and the secondary current as 2782 ampere. Now I have to calculate the prospective short circuit fault current at the transformer level. So what we will do, we will find the transformer impedance. This is the percentage impedance, don't be confused. This is the percentage impedance of the transformer. We have to calculate the transformer impedance. The formula for the transformer impedance is percentage impedance of the transformer into 10 into kilovolt square secondary kilovolt square divided by kVA. So here the percentage impedance is given as 5.48. So I substitute the value 5.48 into 10 into kilovolt for the secondary is given as 0.415. So square of that divided by 2000, which is the transformer kVA. If we will calculate this one, we will come to a value of 0.0047189 ohm. So this is the transformer impedance. Now we have to calculate the prospective short circuit fault current for this transformer. The formula for the prospective short circuit fault current is 1.05 into secondary voltage divided by root 3 into transformer impedance. So we will substitute all the value. 1.05 into secondary voltage is 415 volt divided by root 3 into transformer impedance that we calculated here 0.047189. Then we will calculate this value. Then we will come to know that the prospective short circuit current at the transformer is 53.14 kilo ampere. So we can write here that the maximum prospective short circuit current at the transformer level is 53.14 kilo ampere. It means if we are designing any breaker at the secondary side of the transformer, then we have to choose the breaker which have the short circuit current capacity more than 53.14 kilo ampere. So for that we will choose a breaker which have the short circuit current capacity as 65 kilo ampere, as it is greater than the calculated prospective short circuit current. Now let us calculate the maximum prospective short circuit fault current at the MdB level. So here in our example, as I told you, there is 7 cables of 630 square mm, 2 cable for the red phase, 2 cable for the yellow phase, 2 cable for the blue phase. So total there is 2 runs of cable. Okay. So now let us calculate the prospective fault current at MdB. What are the available data? As we calculated in our previous step, the transformer impedance. So here we have the available data, transformer impedance, the distance between the transformer and MdB. The cable run which is connecting the secondary winding of the transformer to the MdB incomer is 50 meter, that is 0.05 kilometer. The total number of cables are 7. 2 run for R phase, 2 run for blue phase, 2 run for yellow phase, and 2 run for blue phase, and 1 run for neutral. So the total number of runs of the cable is 2 run only. Cable is 7, but the run is 2 only. Don't be confused in it. And the cable size is 630 square mm single core. As per the manufacturer data, we have to check how much resistance or impedance of this size cable per kilometer. You will get it from the cable data technical data sheet. So here I refer the NCI cable data sheet. Here you can see that for 630 square mm XLPE insulated cable, the impedance per kilometer is 0.10 ohm. So I have selected the value 0.10 ohm per kilometer. As we know now from the data sheet that 630 square mm cable is offering 0.1 ohm resistance per kilometer, then we can easily find the same cable 630 square mm cable for 50-meter run how much resistance it will offer. So it will be, the cable impedance will be ohms per kilometer into the length of the cable, that is 50-meter, divided by the number of runs. So the ohm per kilometer is 0.10 and the length of the cable is 0.05 kilometer and the number of run is 2. When we will calculate, the value will come as 0.0025 ohm. It means this 50-meter length cable will offer a resistance of 0.0025 ohm. Hope you understand this one. This is a simple mathematics. Now, in order to find the prospective short circuit fault current at the MdB level, we have to use the same formula which we have used for calculating the prospective fault current at the transformer level, that is I short circuit is equal to 1.05 into secondary voltage divided by root 3 into transformer impedance. Here the only difference is that with the transformer impedance we have to add the cable impedance, because when we are calculating the prospective short circuit fault current at the transformer level, then the impedance of the transformer only in the picture. But when we are calculating the prospective short circuit fault current at the MdB level, then the impedance of transformer plus impedance of cable also coming into the picture. That is why we added the transformer impedance plus cable impedance. When we will substitute all the value, 1.05 into secondary current is 0.415 divided by root 3 into transformer impedance is 0.047189 and the cable impedance which we calculated here 0.025 ohm. Then we will get the value 34.5 kilo ampere. It means the prospective fault current at the MdB side will be 34.5 kilo ampere. So in order to select the any breaker rating at the MdB side, it should have the short circuit breaking capacity more than 34.5 kilo ampere. So we will either choose 35 kilo ampere or 50 kilo ampere, as our calculated short circuit fault current capacity, calculated prospective short circuit current is only 34 kilo ampere. Now let us calculate the prospective short circuit current at the SMDB level. What is the available data? We have the transformer impedance. The distance between the MdB and SMDB is 25 meter. Here this SMDB is far from the MdB by 50 meter. So the cable length is 50 meter. The cable size is 240 square mm XLP insulated cable 1 run. From the technical data sheet of the cable, we can get the impedance ohm per kilometer for 240 square mm cable. Here you can see that for 240 square mm XLPE cable, the impedance value is 0.13 ohm per kilometer, which I mentioned here. 0.13 ohm per kilometer. So impedance of only 25 meter cable, that is Z cable, for 240 square mm cable is ohm per kilometer into the length of cable divided by number of runs. So ohm per kilometer is 0.13. The cable length is only 0.025 kilometer divided by number of run, that is 1. When we will calculate this one, we will get the value of 0.00325 ohm. In same manner, the maximum prospective short circuit current at the SMDB level will be 1.05 into secondary voltage divided by root 3 into transformer impedance, cable impedance between point A and B, that is between point A and B, and the cable impedance between point B and C, that is for this cable impedance which I mention here. The cable impedance for transformer plus cable impedance between point A and B plus cable impedance between B and C. Then when we will substitute this value, we will get the maximum prospective short circuit current as 24 kilo ampere. It means that when we are designing the circuit breaker for this SMDB, then the all circuit breaker should have the short circuit current capacity more than 24 kilo ampere. Now let us calculate the maximum prospective short circuit current for point D, that is for final distribution board. Here the available data is Z transformer which is given, and we calculated in the first step the distance between the SMDB and DB is 65 meter. The distance between this panel SMDB and final distribution board is 65 meter, and the cable size is 50 square mm XLPE cable. As per the technical data sheet, the ohm per kilometer for 50 square mm cable is 0.51 ohm per kilometer, which I mention here, 0.51 ohm per kilometer. So the total impedance of 65 meter cable, which is having a size of 50 square mm, will be ohm per kilometer into length of the cable divided by the number of runs. So ohm per kilometer is 0.51. The length of the cable is 65 meter, that is 0.0565 kilometer. Number of run is 1. When we will calculate this one, we will get the value 0.033201 ohm. Now again, the prospective short circuit current at the final distribution board level will be 1.05 into secondary voltage divided by root 3 transformer impedance, cable impedance between point A and B, cable impedance between point B and C, and the cable impedance between C and D. What does it mean? The transformer impedance, the cable impedance between point A and B, that is for this cable, the cable impedance between B and C, that is for this cable, and the cable impedance between C and D, that is for this cable. Okay, when we will substitute all the value, then we will get the prospective short circuit current as 18.24 kilo ampere. So when we will design the circuit breaker for the final distribution board, then the breaker rating should be more than 18.24 kilo ampere. Now let us calculate finally what would be the maximum prospective fault current for the load which is fed from this final distribution board. So let us calculate the prospective short circuit fault current at load. The available data is Z transformer, and the distance between the DB and load is 80 meter, that is 0.080 kilometer, and the cable which is connecting the final distribution board to the load is 6 square mm XLPE cable. The impedance ohm per kilometer for this 6 square mm cable is taken as 3.92 ohm per kilometer, which is from the technical data set. For 6 square mm cable, the impedance value is 3.92 ohm per kilometer. Now impedance for a 80 meter 6 square mm cable will be ohm per kilometer into the length of cable divided by run of cable. The ohm per kilometer is 3.92. The length of the cable is 80 meter, that is 0.08 divided by number of run, that is 1. So when we will substitute this one, we will get the value as 0.3136 ohm. In order to calculate the maximum prospective short circuit fault current at the load level, then the formula is 1.05 into secondary voltage divided by root 3 into transformer impedance, cable impedance between point A and B, cable impedance between point B and C, cable impedance between C and D, and the cable impedance between D and E, that is from final distribution board to load. When we will substitute all this value, we will get the maximum prospective short circuit current at load as 0.76 kilo ampere. Here I want to highlight one important point, that suppose this final distribution board do not have 50 square mm cable size, it is something else, maybe 25 or 35 square mm cable, and the distance of this final distribution board from the main sub main distribution board is different from this final distribution board, then the prospective fault current for this final distribution board may be different from this final distribution board. It means that the maximum prospective short circuit fault current depend on the distance between panel to panel and the cable size which is connecting these panel. Hope you clearly understood the concept of prospective short circuit fault current. Here we calculated the prospective short circuit fault current at transformer level, which is 53.14 kiloampere. So the standard breaker rating we will select at the transformer secondary is 65 kiloampere, which is higher than the calculated prospective short circuit fault current. At the MDB, we calculated the prospective short circuit current as 34.5 kiloampere. So we will go for 50 kiloampere prospective short circuit current, which is the next standard higher value. For the SMDB, we got the value of the prospective short circuit current as 24.24 kiloampere. Then we will go either for 25 kiloampere breaker rating, short circuit breaker rating, or we will go for 35 kiloampere short circuit breaker rating. We calculated the prospective fault current at SMDB is 18.18 kiloampere. Then either we can go for 20 kiloampere short circuit breaker rating, or we can go for 25 kiloampere short circuit breaker rating. And at finally we find the prospective short circuit current at load is 0.76 kiloampere. So we can go for the load as 100,000 ampere or 1 kiloampere prospective short circuit breaker rating for the load. Hope you clearly understood how the prospective short circuit current is to be calculated at the different. Here I want to highlight one important point, that if the percentage impedance will be lower, then the fault prospective short circuit fault current at the system will be higher. That is why I have chosen the lower value of the transformer percentage impedance to have the worst case. If I will calculate the prospective short circuit current of the electrical system at the value of 6.15, we will get the prospective short circuit current comparatively lesser than the prospective short circuit current when I calculated with the value of 5.48. The motto of this discussion is that when the percentage impedance of the transformer is higher, then we will have the lower prospective short circuit current, and when the percentage impedance of the transformer is lower, then we will have the higher prospective short circuit current for the same rating and the same ratio of the transformer. So it is very important to select the transformer very wisely. If we oversize the transformer, then the prospective short circuit fault current of the system will be high. In that case, we have to increase the breaker rating of each switchgear high, which will cost us more. Moreover to that, it is not technically sound to have unnecessarily the higher short circuit breaking capacity, even if we can make it lower by selecting a proper size of the transformer. This is all about this video. I hope you learn from this video how to calculate the prospective fault current and the necessary concept which required to calculate the prospective short circuit fault current for an electrical system. If you find this video informative and you learn something new from this video, then please give thumbs up and subscribe to my channel. We will meet in any other video. Till then, take care, keep learning, and bye bye. Thank you so much.